Hi class. Earlier in chapter 4 part 2 we took a look at vertical heat imbalances, and now we're going to look at horizontal heat imbalances. Um, I'm making a number line of actual latitudes here, so I guess it's a latitude line. We've drawn this figure, at least the beginning part of it, once before. We were looking at ocean currents and ocean circulation back in section 3C of chapter 4. And so the first part of this is going to look familiar to you. So we've got the equator in the center, we got the South Pole and the North Pole, and let's talk about some of the things that are going on here. And so in the tropics, we find that here we always have high solar noon sun angles. So high solar noon sun angles, those are going to lead to, let's put it this way, tremendous solar intensities. Okay, so tropics are warm. It makes complete sense that they'd have high solar intensities because of their high solar noon sun angles. Okay, as we get out towards the poles, it's pretty much just the opposite. Here you have low solar noon sun angles at the poles. Parts of the year, they don't even have a sun angle. So back from chapter 3, there are times of the year where the poles, the sun doesn't even make it above the horizon. They have 24 hours of darkness, or at least twilight, during certain parts of the year. So low solar noon sun angles when they do have a sun angle. And so this means that they are going to have low solar intensities, or no solar intensities, depending on how you look at it. So lower solar intensities. All right, and so what this is going to mean is that in the tropics then, where you have tremendous solar intensities, the incoming solar radiation is going to be greater than the outgoing terrestrial radiation. Okay, so you're going to build up heat in the tropics. Okay, and so this is going to lead to a surplus in heat energy. In the tropics. Okay, and then in the polar locations, the incoming solar radiation is going to be less than the outgoing terrestrial radiation. Okay, and this is going to lead to a deficit of heat energy towards the poles. All right. Let's see. What was the next thing I wanted to tell you then? So if we have a surplus of heat energy in the tropics and we have a deficit of heat energy in the poles, then somewhere along this number line, it means that somewhere incoming solar radiation has to equal outgoing terrestrial radiation. Okay, and what it turns out to be is right around 32 degrees north latitude and 32 degrees south latitude. Okay, that's where incoming solar radiation equals outgoing terrestrial radiation. Incoming solar equals outgoing terrestrial. So that's where you have a balance of incoming solar radiation and outgoing terrestrial radiation. This took me by a big surprise when I started studying this, because I think about in the United States, the locations that are around 32 degrees north latitude. And we're talking about places like Atlanta, Georgia is at 34 degrees north latitude, so they're even further north. So actually Atlanta has more outgoing terrestrial radiation than incoming solar radiation. So that was a big surprise. But places like Phoenix, Arizona, Mobile, Alabama, Dallas, Texas, Los Angeles, California, those are places that are right around 32 degrees north latitude. Those are places that have a balance of incoming solar radiation and outgoing terrestrial radiation. You know, I think of Dallas, Texas. Oh my goodness, it's 100 degrees in the summertime consistently, and I could never live there. It's too hot and humid. And yet Dallas, Texas is right along that 32 degrees north latitude boundary where the incoming solar radiation equals the outgoing terrestrial radiation. And when I say that, I'm talking about over the course of an entire year, not a day, of course. So, over the course of an entire year, 32 degrees north latitude, 32 degrees south latitude, this incoming solar radiation equals the outgoing terrestrial radiation. Okay, here's something else I wanted to share with you. So this is a figure from the book. It's also on the PowerPoint slides. So the solid line here represents the incoming solar radiation. The dashed line represents the outgoing terrestrial radiation. Okay, and so again, notice 32 degrees north and south. Okay, that's where incoming solar equals outgoing terrestrial over the course of a year. Okay, and within those, within equator word of 32 degrees north and south, incoming solar radiation is greater than outgoing terrestrial radiation. But I also wanted to show you this because there is a tremendous amount of outgoing terrestrial radiation. There is a tremendous amount of outgoing terrestrial radiation. Okay, and that makes sense because if you remember Stefan Boltzmann's law, the hotter the object, the more energy it emits. So the tropics are very warm, so they're emitting a tremendous amount of terrestrial radiation. Okay, but even though the tropics are emitting a tremendous amount of terrestrial radiation, the incoming solar radiation is still greater, and therefore you're building up a surplus. Okay? If you go poleward of 32 degrees north and south latitude, okay, the outgoing terrestrial radiation is greater than the incoming solar radiation, and as a result, we build up that deficit of heat energy poleward of 32 degrees north and south latitude. Okay, so where we're going with this now is now that we recognize that there's a surplus of heat energy near the equator in the tropics, there's a deficit of heat energy poleward of 32 degrees north and south latitude. Okay, so the Earth atmosphere system is going to want to reach equilibrium, so it's going to try to move this surplus heat energy from the tropics out towards the poles. Okay, and that's where we're taking this discussion next. And in fact, I am going to build on this figure. Okay, and so we're going to take a look at how do we move that surplus heat energy from the tropics towards the poles in order to try to reach equilibrium. Okay, that's what's coming up next.